Hello, everyone, and welcome to today's lecture. Today, we're going to start talking about a new pattern, which is sorting. But before we talk about sorting, let me quickly review what we covered in the last lecture. So the last lecture was about merge, and we said that an ordered merge operation is an operation that takes two ordered lists and merges them into a combined ordered list. And one way to parallelize merge is to simply assign a thread to each one of the output each one of the locations in the output array. And that thread is responsible for going and finding which input element it is supposed to be placed in that output array. So here the key challenge is basically how can a thread, given an output index, find the corresponding input indices? And we refer to this as the co-rank. So given an output index, K into the output array C. The co-ranks of K, I, and J are the corresponding indices into I and J. And we observed a few things about the relationship between I, J, and K. We said that J equals K minus I. So the problem is really given K, we just have to find I, then we can easily find J using just applying K minus I. So what we did is we put a bound on K, we put a bound on I, and then we also found a way to figure out if we guess an I, if this guess of I is correct, if it's too large, or if it's too small. And that's based on the observation that A of I minus 1, so the value in the input array A before I, should be less than or equal to B of J, and also the B of J minus 1, the value before J, should be less than or equal to A of I. Otherwise, we would have gotten the element from the other array, not from that array. So really, it boils down to a binary sort within this bounds based on this criteria for checking if our guess is correct, too large or too small. Okay. After that, we observed that this approach is not very work efficient because a sequential merge does O of n operations, whereas this parallel merge approach does O of n log n because we have n threads assigned to n elements, and then each thread is doing a binary search which takes log n operations. So to improve work efficiency, what we said we could do is we could use thread coarsening. And the idea of thread coarsening here is that rather than assigning every thread to one element in the output array, we can assign every thread to a fixed size chunk in the output array. And then that thread will use the co-rank function to go and find the corresponding input segments in the two input arrays, and then merge those two segments sequentially. So the sequential merge is work efficient. And then that way the binary search gets amortized across many elements. We don't have one binary search for every element that we need to merge. We then observed that memory coalescing is very bad over here because the binary search is not very coalesced in terms of its memory access. It has kind of a random access. And then also, after we apply thread coarsening, each thread is going to be responsible for a contiguous chunk of element in the output. So when the threads are writing to the output and also when they are iterating through their inputs, adjacent threads are not going to be accessing adjacent locations in the memory. So to overcome that problem of memory coalescing, we said what we could do is we could use the shared memory. Instead of having all the threads do their binary searches and their merges inside of the global memory, we can instead have instead have one thread in the block find the input segments for that block. Then the threads can load those input segments into the from global memory to shared memory in a coalesced way, and then we can have all the other threads in the block do their binary searches in the shared memory. And then all those threads can do their merges in the shared memory, and then we can write out the final result from the shared memory to the global memory in a coalesced way. So this is what we covered last time. Any questions about parallel merge before we move on to sorting? Everything's clear? Okay, so then today we are going to talk about sorting. Okay, now when we talk about sorting, we're going to look at three different ways of doing sorting on GPUs. Of course, there are many ways, right? A lot of the CPU sorting algorithms that the sequential sorting algorithms that they can have equivalents on GPUs. What's the simplest sorting algorithm that you usually start with when we look at sequential sorting algorithms? Right, bubble sort. So bubble sort is kind of the first algorithm. So let's start by this kind of, obviously, bubble sort is O of n squared, so even on the GPU, it's not going to be very efficient. But let's start by thinking about what a bubble sort could look like on the GPU, or not necessarily a bubble sort, but could it maybe a variant of bubble sort. So what do you think a kind of a parallel equivalent of bubble sort would look like?
What's Professor?
Yes.
What is bubble sort?
So I assume you've taken a kind of an algorithms class or a data structures class where we looked at bubble sort. So the idea of bubble sort is that you keep iterating until the list stops changing. And in every iteration, you do a sweep from the beginning to the end of the array, and then you swap elements that are out of order. So in the first sweep, you keep swapping elements that are out of order. And here you're guaranteed that the largest element in the array will bubble up to the end of the array. And then in the second iteration, you'll do another iteration, and then the second largest is going to bubble up until the end of the array. And then you will do at most, you will keep iterating until you stop converging. And here you will do at most n iterations because every iteration, at least one of the elements is, from the end is going to be in place. But you could end up doing less than n iterations. But in the worst case, where the array is reversely sorted, you're going to do n squared operations. So bubble sort is an O of n squared sorting algorithm.
Oh, okay, thank you.
You're welcome. So you're talking about how to do things across blocks. I want you to forget about that. I don't think about blocks, and right now just think of kind of you want to do a parallel sort, okay? Don't think about what blocks need to do and what let's assume we don't have to worry about synchronization. What would be the something similar to doing bubble sort but in parallel? So the idea of bubble sort is that you keep iterating, and in every iteration you are going to swap adjacent elements, right? So we can do something similar on CPUs, right? We can keep iterate on GPUs, right? We can keep iterating, and in every iteration we can swap adjacent elements that are not ordered. Okay. Now the problem with doing this is that if you launch a thread for every element, and if that element
will get race conditions, no?
Right, exactly. The problem with doing that is if I launch a thread for every input for every element in the array, and then if that element is kind of greater than the one that comes after it, I swap it, I can have race conditions because I could have the same element trying to be swapped by two different threads. So if I want to do something similar, how can I avoid these kinds of race conditions?
Could I
assign one thread?
Assign a thread to two elements?
Right, so we can assign a thread to two elements, right? So I can have a thread be responsible for sorting elements 0 and 1, a thread for elements 2 and 3, a thread for elements 4 and 5, threads for elements 6 and 7, etc. But then here I'm only going to end up sorting the even pairs, but eventually I want these elements to propagate, right, across the list. So what can I do to solve that problem?
Sync threads on another iteration.
Right, so I can do a kind of a sync threads, or I can synchronize, and then I can do another iteration. But in the other iteration, what elements would I sort? So instead of sorting elements 0 and 1, and elements 2 and 3, elements 4 and 5, I would sort elements 1 and 2, 3 and 4, 5 and 6, and I keep alternating between the odd pairs and the even pairs, and this is actually called odd even sort. Okay, so odd even sort is similar to bubble sort in that it's going to repeatedly compare and order adjacent pairs of elements until the entire list is sorted. And the parallelization approach is that every thread is going to be responsible for sorting one pair of elements in each iteration. But to avoid race conditions, we are going to alternate between odd pairs and even pairs so that at no point in time we're going to have the same elements in the list being accessed by different threads to be swapped. Okay, so this would look like this. Let's say I have this input array right here. I can start by assigning a thread to all the even pairs. So here this thread would sort elements 4 and 7, they're already sorted. This one would sort 2 and 3, they're already sorted. This one would sort elements 8 and 5, so these would be swapped, they'll become 5 and 8. And this one would sort elements 9 and 6, they're not sorted, so it will become 6 and 9. Then I will do another iteration, but this time I'm going to assign the threads to the odd pairs. So here, this thread will be responsible for sorting elements 7 and 2, here 3 and 5, here 8 and 6. So this thread will sort them, become 2 and 7. This one will keep them as is, and this one will make them 6 and 8. Then in the next iteration, I'll do the even pairs, and here I'll get 2 and 4 are sorted, 7 and 3 will become 3 and 7, 5 and 6 will stay, 8 and 9 will stay. Then I will do the odd pairs, so here 3 and 4 will be swapped, 7 and 5 will be swapped, 6 and 8 will stay as is. And then I will do the even pairs again, so these are already sorted, 7 and 6 will be sorted. And then in final iteration, I'm going to realize that everything is sorted, and I will stop iterating. Okay? So this is how odd even sort works. Okay, what is the complexity of odd even sort? So in terms of time, I need at most n iterations, right? In terms of work, I need n iterations is assuming that all the threads are going to be running in parallel. And in terms of the amount of work that I do, how much work does it do? I have n iterations. Every iteration I'm going to do n operations. So the amount of work is O of n squared. Okay. It's not exactly bubble sort because I don't have this property where the elements bubble up, where the largest element bubbles up from the beginning to the end every iteration. Okay. So it's not exactly bubble sort because we don't have the property that the largest element will bubble up at the end of each iteration. Okay, but it's kind of in the same family of these O of n squared sorting algorithms, where you repeatedly sort pairs until the whole thing is sorted. Okay. Okay, so let's implement odd even sort. We said it's related to bubble sort. We just kind of explained the whole algorithm, so I'm not going to do that again. But yeah, it's related to bubble sort. Okay. All right. So like we said, what's going to happen is I'm going to have successive iterations, and every iteration I will either sort the even pairs or I will sort the odd pairs. So down here in my sequential code, so here I have a loop, and every loop I'm going to run the sort kernel on the even pairs, and then I'll do another sort kernel on the odd pairs. And I'm going to have this integer over here, 0 and 1, that indicates if we are doing the even pairs or if we are doing the odd pairs. Okay. And we're going to have a flag. I'm going to call it has changed. And for this flag, I'm going to start by initializing it to 0 using this CUDA memset function. And then at the end, we're going to copy it back. And we're going to check if it has changed. And if something changed during this iteration, we're going to go again. And if nothing changed, then we know that we are done with the sorting. Is that clear? Okay, so let's implement the kernel. So every kernel is going to do either here I have my input data, I have the flag that I'm going to mark if the order has changed or not, n is the size of the input. And then here, this flag over here is odd step. That flag is going to tell me if I am doing the even step or if I am doing the odd step. Okay. Okay, so let's get started. So first, every thread is going to identify the element or the first element in the pair that it is responsible for. So let's do an even step first. Okay. In the even step, right, thread 0 is going to be responsible for element 0. Thread 1 for elements 0 and 1. Thread 1 is responsible for elements 2 and 3. Thread 3 for elements, or thread 2 for elements 4 and 5. Thread 3 for elements 6 and 7, etc. So every thread is going to be responsible for which elements? If we think
2 times
about
its index and 2 times its index plus 1.
2 times its index, exactly. So we're going to get unsigned, and I is going to be the first element of the pair that the thread is responsible for, is equal to lockIndex.x times locked_in.x plus threadIndex.x, and all of that times 2. Okay. Okay. Now, if it's the even step, I'm where I need to be. If it's the odd step, what should I do? I should add 1. In the odd step, thread 0 is responsible for 1 and 2. Thread 1 is responsible for 3 and 4, etc. So here, I'm going to write, if it's the odd step, I'm going to add 1. And if it's not the odd step, it's the even step, I'm going to add 0. Yes, so somebody's saying we can add the odd step instead of doing if the odd step, add 1, else add 0. You're right, but I'm just doing this for the clarity of the code. But yeah, you're right, we can do it that way. Okay, great. Now we're going to have to do a boundary check. So I'm going to do if I is less than n. Is that enough? Can I do if I is less than n? Right, I'm going to...
less than n my...
So right, somebody in the class said, and also somebody online, I think you're saying the same thing. So here, at the thread is going to be accessing element I and element
I plus 1.
Okay, so here what we can do is we can write if I plus 1 is less than n. I can also write if I is less than n minus 1. But if I write I is less than n minus 1, and then somebody gives me an array of size 0, I will have, n minus 1 is going to wrap around, it's going to cause a problem. Okay, so, but I mean, chances are somebody's not going to get, if n is 0, they'll probably launch a 0 size grid, so the grid won't launch it. Okay, so now we have our boundary check. Next, what we want to do is we want to launch element, we want to load elements I and I plus 1 and compare them, right? So we're going to do if data of I is less than data of I plus 1. Oops, sorry, no, we want to do if data of I is greater than data of I plus 1. So if the pair is not sorted, what do? We're going to sort it. So we want to swap them. So we're going to write unsigned and temp equals data of I. Data of I is equal to data of I plus 1. And then data of I plus 1 equals temp.
Shouldn't we load the data array into the shared memory?
So somebody asked me, do we need to load the data array into shared memory? We don't really need to load in shared memory because we don't have data reuse here, right? But maybe what we could have done is loaded the data of I and data of I plus 1 into registers, and then compared them and then stored them instead of having to load them again, right? So we know how to do these optimizations. I'm focusing mostly on the logic here, right? It's already inefficient to do odd even sort, so I'm not gonna get stuck on the kind of the data reuse aspects. But yes, you're right. We can load them into registers so that we don't have to load them twice from the global memory. Okay, and by the way, the compiler might do that because in this case, it's actually easy to detect that data of I is being loaded twice. Okay, so after I do the swap, what do I need to do here? There's one more thing I need to do. Right, I have the flag.
Set the has changed
I have the flag, which is the has changed flag, and I need to make sure to set that flag to 1. So here, I'm going to write has changed equals 1. Okay. Do I have a race condition when I'm setting the has changed flag? Yeah, so the has changed flag, any thread that sorts its pair is going to set the has changed flag. So the question is, do I have a race condition?
I think, but does it matter? In the end, it's gonna be equal to 1.
Okay, so I think both online and in person people kind of gave the same answer. And here you're saying, you have multiple threads that are writing, but they're all going to be equal to 1. Okay, so people are saying it doesn't matter. Okay, so on the one side, it is a race condition by definition, because the definition of a race condition is when multiple threads access the same value, and one of those accesses is a write. So technically, this is a race condition. Okay. Now, however, the operation that I'm doing is I'm setting it to 1. So if multiple threads are all setting the same value to 1, then the order in which they achieve this is not important. Okay. And we refer to these kinds of operations as idempotent. It's an idempotent operation. Idempotent comes from math, right? So here, this is an operation where if you apply it over and over and over, it doesn't change. The impact doesn't change based on how many times you apply the operation. So because the operation is idempotent, this race condition is benign. Okay. Now, on the other hand, in C++, the semantics of C++ are that if you have a race condition, the behavior is undefined, right? So technically here, because of the C++ semantics, it's better to use an atomic operation to avoid running into any undefined behavior. The atomic operation, of course, is going to kind of have some overhead because you know it's you're doing an atomic you have a lot of threads will be contending with an atomic operation with the same value. I'm not going to do it because in practice the generated code will be correct in this case, and because of the idempotent operation, the race condition is going to be benign. Okay, but just keep in mind that you know this does result in undefined behavior, and the compiler could kind of do random things here. So the proper practice is to actually use an atomic operation. Now, if you have an atomic operation, you can get by that by doing privatization, and then have only one thread in the block go and update the global atomic, etc. I don't want to worry about all that right now, so I'm just going to leave the code the way it is. Any questions? Somebody's asking, because of the undefined behavior in C++, could C++ head to 0? Yes, it could. But I'm saying that in practice here, the compiler is not going to do that. But in principle, because it's undefined behavior, the compiler could do that. So you shouldn't do what I'm doing. You should use an atomic operation. Okay. Okay, great. So I'm going to compile and I'm going to run, but I think the system is busy, so I don't think it's going to run. So we can leave it there and come and see at the end of the course if it is running. Yep. So like as expected, I think the system is busy, so it's not going to run. But we can move on. Okay, so this is odd even sort, and this is the code that we just wrote. Okay. Now, as we said, the complexity of odd even sort is O of n squared, and you know when we do sorting, we don't like to have O of n squared. I mean, if the array was very small, right, then the simplicity is kind of makes it okay. Fine, we'll do O of n squared. If I'm sorting an array that's 8 elements, okay, I'll do a O of n squared sort, right? It's not that expensive, right? But if I'm sorting a very large array, I never want to use algorithms that are O of n squared. Okay, so we want to kind of we'd rather use a sorting algorithm that has better complexity than that. For example, the merge sort, right? So we can use merge sort. What's the complexity of merge sort? Merge sort is O
log n.
Log n, exactly. So what we could do instead is we could use merge sort. Okay, how can I parallelize merge sort? Well, the good news is, what did we do last lecture? Yeah. We parallelized the merge operation, right? So if I know how to do merge in parallel, how can I parallelize merge sort? If I start from my split arrays, right, I can do a parallel merge across many arrays. I can do many merges, and I can do all the merges in parallel, and then I can parallelize within each merge. And then I can keep iterating as my arrays get larger. I have fewer arrays to merge in parallel, but then larger merges to do that I can parallelize within.
Professor,
yes.
This sounds like a reduction problem.
Yes, I mean, yeah, you can think of it structurally as kind of a reduction. You're right. There is kind of a tree-like behavior. I mean, merge sort itself, has a tree-like pattern. So merge sort sequentially divides the list into sublists, sorts them, and then repeatedly performs a merge on the pairs. So what we can do is we can take our input, we can divide it into small arrays. We can sort these small arrays however we want. We can use maybe a simpler sort, like odd even sort, for example. Okay, and then what we can do is we can start doing the merge sort. So we can merge every pair of arrays into a bigger array, and then we can do another merge, and then we can keep merging until we have the largest array. So this is how merge sort works. Okay, and like we were saying, if I want to parallelize this, what can I do? I know how to parallelize
Assign a thread to
individual
each pair.
merge operations, right? So I can use the merge that we implemented last time to parallelize this one merge operation, and then I can do a lot of these. These are all independent of each other, so I can do a lot of these trivially in parallel. Okay, so the parallelization approach is we can assign a thread to each element. In this case, the threads can do a simple sort of each array, and then they can start doing merges. And in the earlier step, I'm going to get a lot of parallelism from across merges and a little bit of parallelism within merges. And in the later step, I'm going to get a lot of parallelism within the merges and a little bit of parallelism across the merges. Is this clear?
Professor,
Yes.
fourth step, the one just last before the final merge. When we have two merges at the same time, so for example, the merge on left is we have 4 threads working on it or only one?
So here on this left, you're going to have half your blocks working on the merge on the left. You'll have half your blocks working on the merge on the right.
So 4 by 4.
You mean 4 blocks, 4 threads? Yeah, I mean, yeah, for illustration purposes, I'm drawing 4 blocks and 4 threads. But of course, the block is going to have much more threads than 4. Yeah, but yes, you're right.
Oh, the whole threads or whole block. Oh, okay, whole blocks. Okay.
Yeah. Okay, so what's the complexity of this? So in terms of time complexity, how many iterations will I have? I'm going to have log n. So if all my threads actually run in parallel, I need log n steps to finish. In terms of work, I'm going to have O of n log n kind of operations. Of course, assuming that this merge itself is n, but it didn't, right? We saw that this merge is actually n log n. So it's actually going to be something closer to O of n log squared n. Okay, because we said that the parallel merge itself is not work efficient because we have that binary search that creates a log n factor. Okay. Okay, so we have merge sort has a complexity of O of n log n, and you know this is the best that we can achieve for a comparison-based sort. Okay. Now, if I want to sort with a complexity that's even better than O of n log n, what can I do? I can't use comparison-based sorting, right? A comparison-based sort is going to, the best you can do with a comparison-based sort is n log n, all right? So what sorting algorithms are more efficient than that? So somebody
Bucket
says bucket sort, right? Bucket sort. So in general, we want to, if you want to have better complexity, we want to have a non-comparison-based sort like bucket sort or radix sort. Okay, so let's talk about radix sort. Okay, so let's say we want to parallelize radix sort. So how does radix sort work? The way radix sort works is I sort I distribute my keys in 2 buckets, right? Based on some radix value. So I take my keys, I extract a radix value from these keys, and I sort them onto buckets based on this radix value. And then I keep, I keep repeating this process. So I keep taking a different radix value or digit, right? So you can think of it as a digit. I keep taking a different radix value, and then I sort by that radix value while preserving the order from the previous sort. And I keep doing that until I've iterated over all my digits, and then by that, once I do that, my sorting is done. Is that clear? Okay, so to simplify things, we can usually use radices that are a power of 2 because that makes it easy to take our key and divide it into chunks where we can easily extract the digits. So this makes it easy to slice the bits from the key. So what we're going to do is we're going to start by using a radix of 2. In other words, we're going to use a 1-bit radix, and then we're going to improve on that. Okay. So for example, if I have this set of keys over here, they're 4-bit values, and I want to use radix sort in order to sort these. The way I would do that, I can start from the largest bit, work my way down, or I can almost even work my way down, or I can start from the least significant bit and work my way up. Let's start from the least significant bit and work our way up. So here, what I can do is I can look at the least significant bit of each of my keys. And then I will separate my keys into buckets based on the value of this least significant bit. So I'm going to take all my keys whose least significant bit is of 0. I'm going to put them next to each other in a bucket. And then I'll take all my other keys whose least significant bit is 1, and I will put them also next to each other. Okay, so I've taken my elements and I have partitioned them into 2 different sets. What does this look like? Does this look like a pattern we've already covered? Filter, right? So last lecture we talked about merge, lecture before we talked about filter. That order was intentional, right? So here, when I'm taking all the values whose bits are 0 and I'm putting them together, I'm doing a filter operation. So here I'm doing actually a multi-filter, or we also call this a partition, which is a generalization of filter, where I don't just filter element keys that meet one criteria, I filter different keys that meet different criteria into different buckets. Okay? All right, so after I've done this, now I move on and I look at the second bit, and then I will go and I will partition my keys again based on this second bit. So I have the ones whose second bit is 0, the ones whose second bit is 1. But I will retain the order from the previous iteration. So is this a stable filter or an unstable filter? It's a stable filter because I need to retain the order. This is where the need for stability comes from. So now if you look inside of each one of these buckets, the elements are sorted by both the first bit and the second bit. I have the 0, 0, and then I have the 0, 1s, and then I have the and then here I have the 1, 0s, and then I have the 1, 1s. So now all my elements in the list are sorted by the least significant 2 bits. Next, I will move on and I will look at the third bit, and I will partition based on the third bit. Now my elements are sorted by the lower 3 bits. And then finally, I will look at the most significant bit and I will partition based on the most significant bit. And once I partition based on the most significant bit, now my entire array is sorted. Okay? Is this clear? Any questions?
Professor?
Okay, great. Yes, somebody has a question.
Yes, the reason we needed a non-comparative algorithm such that we avoid synchronizing between different warps.
No. We're gonna have to synchronize here, and we're gonna have to synchronize in the merge sort. Here, I'm just trying to show you different classes of algorithms. I showed you how to parallelize one kind of non-comparison based sort, like merge sort, and here I'm also showing you how to parallelize a non-comparison based sort like radix sort, right? Which one we will use? I mean, it depends, right? Not every key can be kind of sorted using radix sort, right? You may not be able to extract different kind of radices from a key, right? You might have a comparison operator that they're using for sorting that's complex, and if you have a complex comparison operator, you might have to use a comparison-based sort. You can't use a non-comparison-based sort. But if you're sorting integers, right, you can easily use radix sort instead of merge sort. Is that clear?
Yes, thanks.
Yeah, you're welcome. Okay, great. So how do we parallelize this? Well, obviously the iterations are going to have to happen sequentially, one after the other. So we're going to parallelize each one of these operations. The question of how to parallelize radix sort is really, how do I parallelize one iteration of radix sort? Okay. So how do we parallelize this? Okay. And to parallelize this, the real question is, I can assign a thread to every one of my input elements. That thread can be responsible for going and writing that input element to the right place in the output array. So really the question is, how do I find the destination of each element in my input array? Now
Could we count how many numbers have the bit as 1 versus 0? Because that
so
would
somebody in person said binary search. We can't use binary search here because it's not like the merge operation, right? Actually, we can do something simpler, which is what we did in partition. So somebody online mentioned, we basically need to count how many elements before each element have a 0 or have a 1. Okay, and this is what we did in filter. Remember, in filter and stable filter, we counted how many 1s are there before. Here we need to know how many 1s, how many 0s. All right. Okay, so how do I find the destination of each index? Well, if the radix value is 0, then the destination of 0 is basically counting how many zeros I have to my left. Correct? If the radix value is 1, then the destination is going to be the total number of zeros plus the number of 1s that I have to my left. Is that clear? Okay. Now, the number of zeros to the left is going to be the total number of elements to the left minus the number of ones to the left, correct? And the total number of elements to the left is just the index of the element. So here, to get the destination of a 0, I need to just find the number of ones to the left and subtract that from my index. Okay? The destination of a 1 is number of zeros in total plus ones to the left. The number of zeros in total is the total number of elements minus the number of ones in total. So total number of elements minus the number of ones in total. The total number of elements is basically the input size, which we know. And the number of ones in total is basically the number of ones to the left of the last element, plus whether or not that last element is a 1, right? So we can easily find that. So really, this problem boils down to counting how many elements with radix 1 exist to the left of an element. And how can we do that?
A scan.
Right, with an exclusive scan, just like we did in the case of filter. Okay? So to find the destination index of each element, we're going to first start by extracting the bit that we are interested in for that iteration. We're going to run an exclusive scan on that bit. And then depending on whether the original bit was 0 or 1, we're going to find the destination. Based on whether it's 0 or 1, we're going to use the right expression to find the destination. And then once we have the destination of each element, each thread can then go and write its element to the destination index that it found. Is this clear? Okay, so the parallelization approach is trivial. We can simply assign a thread to each element. The thread is going to kind of perform this computation. The exclusive scan is going to be performed across all the threads, and then we write our final result. Any questions? Yeah, so somebody's asking, could I have a race condition here if we're not using two different buffers? You're right. So this here has to be an out of place operation. Okay. Now, because of the scan, I'm making sure that earlier threads are reading before later threads. But in this case, that's not enough because over here, right, the earlier blocks are going to write before the later blocks read. So a unidirectional synchronization isn't enough to enforce this. In the filter, right, I was going in one direction. So unidirectional synchronization was enough. But here, the unidirectional synchronization is not enough because I'm sending elements in both directions. So in this case over here, I'm probably going to use out of place. But if I want to use in place, I need to have a barrier, which is going to limit the number of blocks they can have, which is going to limit the size of the input array that I can. Okay, great. So now we know how to parallelize radix sort. Okay. What about efficiency? What's kind of not very efficient about all of this? We're going to have to do it multiple times. We'll see later on how we can reduce how many times we do it, obviously by making the radix larger. Okay.
The writes to the destination are not coalesced?
Right, exactly. I have a very bad problem when it comes to memory coalescing. If I look at what adjacent threads are doing, adjacent threads could be writing to very different locations in memory. Okay, so here, one of the main challenge is that my stores are not coalesced because nearby threads are going to be writing to distant locations in global memory. Okay, is that clear? Okay, so given that, what do you think we can do to improve the coalescing behavior?
Shared memory.
We could
Yes? Somebody said
Shared memory.
Yes, you're right. Is that what the other person wanted to say?
I wanted to ask if we could load everything and then figure out the index and then reassign the threads to the stores.
So yes, and to be able to reassign the threads to the stores, we're going to have to use shared memory, exactly. So what we can do is we can first have every block sort its own array in the shared memory. That way we divide up the keys between the ones going into the first bucket and the ones going into the second bucket. And then we can write out each one of those buckets in a coalesced way. Okay, And that looks like this. So first, what we will do is we can have bring these elements into shared memory. We can, instead of doing a global scan across all the blocks that does kind of a global sort, I can start by doing a local sort inside of each block. So every block is going to divide its elements into 2 buckets, right? Each block does that on its own inside of the shared memory. Okay, and now every thread, every block now each block has a contiguous first bucket and a contiguous second bucket. It can write those buckets out in a coalesced way. And in this case, adjacent threads will be writing out adjacent elements into the same bucket. And we're only going to have one case in the middle, right? If these buckets happen to fall not on the boundary between 2 warps, we're only going to have one warp that would, be writing it to 2 different places. But all the other warps will all be writing to contiguous locations in memory. Okay. But now the challenge is, how does each thread know where to write out its bucket? If I sort locally, so here when I sort locally, I'm going to do the scan locally, right? I'm going to do a block-wide scan. I don't need to do a global scan. But in order for eventually each thread to know where it needs to write out its bucket, what do we need to do? We need to do a global scan. But now, rather than having a global scan with all the elements in all the threads, every block is going to contribute only 2 values to that global scan. And let's take a look at what that looks like. So here, in the first block, I have an element, this bucket is of size 2, this bucket is size 2. Next, here I have bucket of size 2, bucket of size 2. Then I have bucket size 1, bucket size 3, bucket size 3, bucket size 1. The way that I want to order these buckets is I want to put this bucket first, and then this one, and then this one, and then this one, right? And then this one, and then this one, and then this one, and then this one, correct? So to be able to figure out where each bucket should go, I should arrange these bucket sizes in that order and do a scan on the bucket sizes. So here, every thread block is going to write out its bucket sizes. So here I have for each block and for each bucket, in this case, I have 2 buckets, the 0s and the 1s. It's going to write out the size of the bucket. And then I will take this array, I will think of it as a linear array, and I will do an exclusive scan on that array. And then after I do an exclusive scan on that array, now I have for each block where its 0 bucket is going to start in the global memory and where its 1 bucket is going to start in the global memory. Okay, and then the blocks read that back, and now every block is going to know where its elements are going to start. And now each block can go and can write out its elements from the global memory to the shared memory in a coalesced way, right? And if we here focus on the first block, see how its writes are happening, you'll notice that I have all the elements going to the 0 buckets are contiguous, and then I have the elements going to the 1 bucket are contiguous. So here I have better coalescing when I'm writing out the first bucket, better coalescing than when I'm writing out the second bucket, as opposed to what I had before, where adjacent threads could have each been writing 2 different buckets. Is this clear?
Professor?
Wait, I have a question in person, and I'll take the questions online. Yes. So somebody's observing that if we increase the radix value, we're going to have this problem is going to become worse, the coalesced problem, and you're right. And we'll observe that in a bit. But yes, you're absolutely right. Okay, and another question online?
Professor?
Yes.
Here regarding, you said they are coalesced bus threads, right?
So here, the coalescing. So what's going to happen here is I have all the elements in the 0 bucket are going to come after each other, then all the elements in the 1 bucket. Okay. So if I have many warps in my block, most of the warps are going to have do a coalesced, right? Only 1 warp could land kind of at the boundary between the 2 buckets, and that warp may have to do 2 transactions instead of 1 in order for it to store out all its elements.
Yes, but that I mean in not perfect coalescing still.
Yeah,
right?
it's not perfect. I mean, even within the block, it may not be perfect because the warp could land, the bin here could land not aligned to the DRAM burst, right? It could be at the end of one DRAM burst, the beginning of another, right? But the worst case here is going to be each warp is going to do 2 transactions, as opposed to before, where the warp could have to do even more than that when the axes are not coalesced. Okay. Great. So here our stores are coalesced because the nearby threads are going to write to nearby locations in global memory. Okay. Okay. So we've seen how to parallelize a radix sort when our radix is 2, or when our radix has 1 bit, 0 or 1. Okay. Now let's look at, but what's the problem with when the radix is just 1 bit? If I have 32-bit keys, how many iterations do I need? 32 iterations. Like, that's a lot of iterations. Okay. So if I want to reduce the number of iterations, what should I do? I need to increase the radix. So here, if I have a 1-bit radix, I'm going to have n iterations if my keys are n bits long. If I want to have fewer iterations, I can use a larger radix. If I use a larger radix, I'm going to have fewer iterations. But what's the disadvantage of using a larger radix? Can I use a radix of n? Can't use a radix of n, obviously. The problem with using a larger radix is I'm going to have more buckets, and more buckets means less coalescing. So I have more buckets, which means I'm going to have worse memory coalescing, and also I'm going to have a larger scan, because the scan that I'm going to do depends on the number of blocks, but also the number of buckets, which is 2 to the power of the radix value. So obviously, I can't have 2 to the power n buckets, right? I can have a bucket for every possible value in my range. Okay. Okay, so here the choice of radix value must balance between these two things. It must balance between the number of iterations versus the efficiency of the iteration itself in terms of coalescing and in terms of the size of the scan and the number of buckets. Somebody's asking if the square root of n is a good size. I mean, this is something that you can usually tune. It depends on the radix, depends on hardware. Something you can usually tune. Okay, so let's do an example with a 2-bit radix. Let's say I have a 2-bit radix. With a 2-bit radix, I'm going to look at the lower 2 bits. So the lower 2 bits can be either 0, 0, 0, 1, 1, 0, or 1, 1. So how many buckets am I going to have? I'm going to have 4 buckets. So I'm going to have to take these values and I'm going to have to partition them across 4 different buckets. So this is a multi-filter or a partition operation, but this time we're using 4 buckets. Okay. Now that my elements are sorted by the lower 2 bits, now I want to sort them by the upper 2 bits. Of course, it's a stable filter. I need to retain the order. So I look at now the upper 2 bits, and I go and I partition my elements based on the upper 2 bits. And now my whole array is sorted. And what you realize here is we finish, well, how many iterations did we need? 2 instead of 4 in the previous example. So here, because we have a 2-bit radix, we needed n over 2 iterations if we have n bit keys. Okay, so now the question is, if I want to parallelize a radix sort with this multi-bit radix, how do I parallelize? Obviously, the iterations are still going to happen sequentially. So the question boils down to, how do I parallelize across, parallelize one of these iterations? So to parallelize one of these iterations, naturally, I can assign a thread to every element, and we can do the same thing for coalescing purposes. We can have every thread block do a local sort, okay, and then we can have the thread blocks after that figure out where their buckets go in global memory and write to global memory. How do I do a local sort? Now let's focus on one thread block. How can a thread block do a local sort based on 2 bits as opposed to 1 bit?
It's now.
It was easy, right? I had to count the zeros, count the ones. I do a prefix sum.
Now it's 0, 1, 2, and 3.
Right, now it's 0, 1, 2, and 3. So if I want to find out where a 1, 1 goes, I need to count the number of 0 zeros, the number of 0 1s, and the number of 1 zeros in total. And then I have to count the number of 1 1s to its left. Okay. That sounds like a complicated thing to do. We're going to do that actually across blocks, but within the block, we're going to do something simpler, right? Remember, the whole point of using a larger radix, sorry, that's not what I want to say. The problem with having a lot of iterations is because every iteration, I'm going to launch a new kernel. I'm going to bring the data from the global memory to the shared memory. I'm going to write out the data from the shared memory to the global memory. That's a lot of work. But within the block, the sorting is happening inside of the shared memory, correct? So in this case, right, having kind of many iterations versus few iterations isn't too big of a deal. So what we will do with each the local sort is we'll actually use, so here for the local sort, we want to take these, we want to sort them into buckets based on 0, 0, 0, 1, 1, 0, and 1, 1. What we can actually do is we can do multiple 1-bit steps. Okay, so we'll do, within each block, we'll do multiple 1-bit steps in order to get the 2-bit or the 3-bit or the 4-bit sort. Okay, and that's because we're using shared memory, right? The prefix sum is very quick, and you know, we can do that efficiently. Okay, great. So now every thread block is going to sort its elements into 4 buckets. Now the question is, where is each thread block going to write out its bucket from the shared memory to the global memory? What operation do I need to figure that out? An exclusive scan, exactly. So where does each thread block write its bucket? We're going to use for that an exclusive scan. So here, every bucket knows, every block knows the size of each one of its buckets. What I want to do is I want to put this bucket first, and then the 0, 0 bucket from the next block, and the 0, 0 bucket from the next block. We don't have any here, so the size is 0. Then the 0, 0 bucket from the next block, and then I want the 1 here, and then the 1 here, and then the 1, so the 0, 1 bucket here, the 0, 1 bucket from here. We don't have any in this case. Then we have the 1, 0 bucket in each one, and then the 1, 1 bucket in each one. So here, we're going to have to take the sizes of the buckets. We're going to put them together. Right here, I have the block index, and then here I have the buckets. Okay, and now I have the size. I'm going to flatten this array to where I have the buckets that are the same radix value next to each other. And then I'm going to sort them by sort these sizes by the increasing radix value of the buckets. I do an exclusive scan on this. And now that gives me the starting location of each one of the buckets. After I do that grid-wide scan, now each thread knows where its bucket is going to start. And now each thread block can go and write out its local bucket to the global bucket at the correct location. Somebody has a question? Somebody's asking, why are we sorting? What do you mean, why are we sorting them? We're not sorting them. Where do you mean? Here? Yeah, we have to do an exclusive scan to figure out. Here we know the size of each bucket. The exclusive scan tells us where the bucket should start. Oh yeah, no, we're not doing any sorting before the bucket comes. Okay, great. And as you can see, yes, question?
Within the block, when we're sorting locally with multiple 1-bit steps, we do this with we do a local scan like we were doing earlier, yeah?
Yes, we do a block-wide scan.
Yeah, a block-wide scan, and then we do this, so we have a larger number of iterations. So we have double the iterations for 2-bit, right?
Yes.
Okay.
So for 2-bit, we're gonna have to do 2 local scans in order for us to do the sort. Okay.
Yes.
Okay. Okay, great. And as you can see here, if you look at what one thread block is doing, our stores are coalesced because we have the everything, you know, the adjacent threads are going to be storing adjacent buckets from the shared memory to the global memory. And only the threads the warps that fall on the boundaries between buckets are going to have kind of uncoalesced accesses. Okay. But we have more buckets. And since we have more buckets, we have more boundaries between buckets, which means we're going to have more warps that are going to have uncoalesced accesses. Okay. And when I had the 1-bit radix, I had fewer buckets. Each bucket was larger. So I had more coalescing opportunities. When I increased the radix value, Now I have smaller buckets. So I have more buckets, and each bucket is smaller. So my coalescing is bad again. Okay. So what can we do to overcome this problem? If we have these small buckets, we have a lot of these buckets, they're small. If I want to kind of go back, reduce the number of buckets, make the buckets larger, have fewer of them, what can I do to solve this problem? Improve that coalescing. So someone is asking, can I have kind of multiple kind of block size elements come together within the same set of buckets? And yes, we can by doing thread coursing. So here, the cost of parallelizing the work across multiple blocks is that each block is going to have its own set of buckets that it's going to need to write from the shared memory to the global memory in a coalesced way. If these blocks are running in parallel, great. If the blocks are not running in parallel, then it's actually better to consolidate these elements into fewer blocks so that each block is going to have larger buckets. That way, the transfer of these buckets from the shared memory to the global memory will be more coalesced. Is that clear? Okay, so the price of parallelizing across more blocks means we have smaller buckets, and therefore we're going to have fewer opportunities for coalescing. There's also another price of parallelizing across more blocks is the scan. The more blocks I have, the larger the scan operation that I need to do. So what we can do is we can process more elements per bucket, and this gives us larger buckets per block, and therefore better coalescing. So this would look like this. Here, instead of each thread being responsible for one element, each thread can be responsible for multiple elements. This way, the thread block itself does a local sort. Remember, the local sort is going to do scan operations. And scan also has work inefficiency issues. And if I have the thread block responsible for more elements, that scan operation is going to become more work efficient. Okay. And then after that, each thread block is going to write out its elements from its buckets from the shared memory to the global memory. And notice here how we're going to have more or better coalescing opportunities when we are writing out the buckets because the buckets are larger. So by applying thread coarsening to this partition operation, right, we improve the work efficiency of the scan operation, and we also improve the memory coalescing of writing out these buckets. And by the way, if you remember, this was the same thing when we covered stable filter. Remember when we covered stable filter, the problem with stable filter was coalescing, right? And the scan operation. And we applied thread coarsening to improve the work efficiency of the scan and also to improve the memory coalescing. I think I rushed that lecture when we covered stable filter. We're running out of time, so I kind of rushed that concept. But you can go back and review it because here it's the same exact behavior for the same exact reason, right? This is a form of packing where we are taking these elements, we're packing them into larger contiguous buckets and then writing them out from the shared memory to the global memory in a coalesced way. Is this clear? Any questions? Okay, if not, that's all for today. We're done talking about sorting. Oh, we have a job running. Let's see, it's still running. Yeah, still running. So unfortunately, you won't be able to see the performance, but it doesn't really matter because we weren't implementing kind of successive their performance. So that's all for today, and I will see you next time. Next time we'll be covering yet another. Actually, next time we're done talking about patterns, and we're gonna talk more about different kinds of application domains. So next time we will be talking about sparse matrices, and then after that we're gonna start talking about graphs. Okay. So these simple patterns that we've been looking at, we're kind of done covering those patterns, and next time we're gonna start looking at advanced patterns and applications. So we're done with part 2 of the book, and now we're moving on to part 3 of the book. Okay. All right. See you next time. Yes.
What do you have for quiz 2 material? Till which chapter for this only?
So now because of the war, I've kind of put a hold on the exam because a lot of you are unable to attend. Okay, so let's see how let's see what's going to happen, and based on how things plan out, we'll see if we're going to have a makeup exam, if we're going to merge that with the final, and also we'll see we'll see, and that then depending on what we do exactly, we'll see what material will be in which exam. If we do have our second exam before the final, it will cover up until the lecture we covered today. So this would be the last lecture for the second exam. But if we don't end up having a second exam, then this material will be also covered in the final. Okay, so let's just wait and see how things turn out, right? And the important thing is that for now that everybody stays safe.
Professor
Thank you.
Yes.
قد ايه عم بيكون in class attendance ليش؟
So the online people are curious how many people are attending in person. Usually we're having, out of 40 students, around I think 4 to 6 people are able to attend in person. I think the rest of you, the majority are being online.
Okay, thanks.
Okay. Thank you all, and I will see you next time. Bye, everyone.
Thank you. Bye.